Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hope you guys are doing well. Hopefully the test also went well for you guys. So you should expect the grades on that in about a week-ish. So towards earlier next week, I'll have those grades for you. And very shortly after that, I'll be doing things like putting you guys into your groups and maybe even start talking about the project that you guys are going to be working on. So that'll be cool. But for now, let's actually just move on. We're going to jump into a whole other topic, a whole new topic, actually. I don't really think I have anything else to announce, so let's just actually do it. So let me make sure that I can see the chat here. Okay. So we are going to start talking about some basic set theory. So the remainder of this class is going to go something like we're going to do sets and counting, kind of think of those in the same thing. We're also going to do probability and then statistics, and then we're going to wrap it up. We're not going to go very far into any of these, but we're going to go far enough for you to have a very basic fundamental understanding of these things. As such, I really want to make sure that we're all on the same page, that we all fully know all of the definitions, all of the concepts. So I'm going to start from the very beginning, very basic, give you guys all the definitions and build up everything from the ground up. And so the next class or two, today's class and also a large chunk of tomorrow's class is going to be me pretty much just somewhat doing a kind of information dump on you guys. But it's going to be important concepts for later, because especially when you get to probability, probability is a subject that can get quite confusing if you don't know how to conceptualize things very well. And knowing how to conceptualize things in terms of sets and tuples, which we'll talk about, is going to be very important for probability. And so knowing about sets and how to construct them and how they work and how they behave is going to be very, very important. So it also going to involve a lot of counting. So this is why knowing how to count things relating to sets is also going to be very important. So yeah, we are going to talk about sets, what they are, how to visualize them, how to do mathematical operations with them, how to count their elements, and all that good stuff. We're not going to do all that today. In fact, we're going to, but we're going to try to get as far as we can. In the last class, I got up to about where we were talking about power sets. So I think we are going to end roughly the same place to keep things consistent. But as for that, I'm just going to give you the definition. It's not really stuff to figure out. It's just kind of stuff to know. So if you want me to clarify a definition, you can stop me and ask me. But for the most part, it's just certain things that are, this is just what we call them. This is a matter of fact. It's not, there's almost no real reason why these things are the way I'm saying. It's just how we think of, how we define them. Okay, so we're going to go through a lot of definitions, and that'll be today's and tomorrow's class mostly. So let's begin. This is actually this is actually from section 7.2 of your text, which talks about sets. So let's actually just talk about, well, what is a set? So definition. A set is an unordered collection of objects. These objects are called the members or elements of the set. When listing members of a set, repetitions ignored. So what is a set? It's an unordered collection of things where if you repeat any one of those things, the repetition is ignored. That's basically what a set is. We will use collection and objects very generally. So a collection is just like a group of things, although group is a bad word to use because it actually means something in math to use the word group, which is not what a set is. So it's just a gathering of things, a collection. So we'll use collection and objects very generally. Could be numbers, could be letters, could be names, could be categories, could be colors, could be whatever. It's a collection of objects, collection of stuff. And there are contexts in which we don't want to have the order mattering, or we don't want to count repeats. So for example, the set of amenities at a particular Airbnb, right? So this is a collection of things. So you can be like, hey, I got this Airbnb, I got Wi-Fi, I got heating. And you're like, well, you just listed the same amenity twice. I mean, I don't think that should count. Like, it's not like you had 3 amenities. You actually only had 2. You just repeated one. Like, there's no reason why I should count that as an extra thing. So you can say, oh, I have Wi-Fi, and I have Wi-Fi, and I have a TV, and I have heat, right? So here, Wi-Fi repeated is not a new amenity. You would ignore it. Right? Also, there's no inherent order to this, right? You can't just say like, I mean, it would depend on the person, right? You can't just say, oh, Wi-Fi is definitely number 1. Like, anyone on the planet would agree that Wi-Fi has to be number 1, or, oh, anyone on the planet would agree that having a TV in the room has to be number 1. It has to be the first thing. It's the most important. Like, you can't really say that. There's no intuitive order, or I should probably say intrinsic order, maybe. It's another nicer word, intrinsic order, right? So it's not like there's a first amenity and a second amenity and a third amenity. There's no reason why the amenities need to be ordered. Also, if you repeat an amenity, you're just trying to beef up your Airbnb profile to say you have 4 amenities when you actually have 3, right? So, so a set is meant to abstract a collection of things where we want to ignore repeats and we don't care about order, because there are times when we want to be able to do this. So let's actually talk about notation is the next thing I want to talk about. How do you actually write down a set? So sometimes we call a set by an uppercase letter. So here, sets can be named usually with letters and usually uppercase letters. Not always, but very, very usually, right? And one way to actually describe what a set is to actually write down, list its members in these curvy brackets. So you can talk about the set A having A, B, C, D, E, F in it, right? So this is list elements in A in curvy braces. This is called the roster method. Okay, so that's called a roster method. That's one way you can represent a set. Now, there are modifications to this method. So for example, I could say, this is the same as A, B, C, dot, 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 right? I can say that, A, B, C, dot, 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 and then I put an F at the end. And basically what that means is that I can use ellipses can be used to represent members that are not explicitly stated, but are obviously included, obviously in quotations here. So sometimes you might want to write out a set, but there are a lot of things in it. Maybe you want to write out the set of the first 1,000 whole numbers, like first 1,000 positive whole numbers, 1, 2, 3, 4, 5. You don't want to literally write down 1,000. So what you would do is you write 1, 2, 3, 4, 5, comma, dot, 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 comma, 999, comma, 1,000, right? So you can write down something that everyone would understand. Oh yeah, he means the set of the first 1,000 positive whole numbers, but you don't have to actually write it out. And so you can use ellipses to represent this. Another way to actually represent a set is via some sort of description. So we can say it's the set of all X such that this is red such that it's the set of all X's such that X is a letter of the English alphabet between A and F inclusive. Right, so here, without actually listing a set, I can actually describe it in words. Maybe the set that I care about, it's hard to actually even list examples of things that are in it, or to list the examples in such a way where it would be obvious to anyone reading it that, oh, I know exactly who are the people in this set. So sometimes you might want to just write out a description. This description is called the condition. Okay, so that's the notation of a set. You can call them by big letters. If you want to kind of list the elements, you can use something called the roster method. You can modify the roster method with ellipses or with descriptions if you don't want to actually physically write out everyone. And so you'd probably use ellipses if it's kind of obvious what pattern you're trying to get the reader to understand, but you can also use a description. So in the above, the members of A are, you know, A, B, C, D, E, F. We can express this via the notation, something like this. I can say A is an element of A. A is a member of A. So this is, say, a member of an element of A is in A, right? And so I would write that symbol. If something is not a member, we use the letter G was not in A. We write that symbol, but then we write a strike through that symbol. So this is saying G is not a member of A. So that's the notation for saying that something is in a set or not. What else do I want to tell you about? So much. I wrote down all the terms I wanted to define for you guys to make sure. Okay, definition. Sets A and B are called equal if they have precisely the same elements and we write A equals B in this case. So a set is uniquely and precisely determined by its members. That's a definition that conceptually you can run into problems with in higher level mathematics, but it's very intuitive. It works at this level. So we are going to stick with it. So for example, if I say A is equal to A, B, C, D, E, F, and I say B is equal to B, B, A, E, F, D, C, E, then A equals B. They're the same set, right? Because remember, sets do not care about repetitions. So the fact that I repeated lowercase b twice and I repeated lowercase e twice is irrelevant to me. I would ignore those repeats. It's the same as writing them once. Also, sets do not care about order. So the fact that A is the first thing in the set big A and A is not the first thing in the set big B is irrelevant to us. I don't care about the order. Are you guys hearing me? My screen just kind of spazzed out for a while. I think you guys are still there. So they're the same. Why are they the same? Because ultimately they contain the same members. They have lowercase a, b, c, d, e, and f, right? They both have all the same things. The fact that they're written in a different order and sometimes I repeated one where sometimes I didn't, those are irrelevant. And the thing is, why would anyone just for the heck of it do this with sets? It turns out they wouldn't. However, remember, a set is an abstraction for things. You want to do math with things in the real world. There's no guarantee that when two different people are researching the same thing in the real world, that they will encounter examples of that thing in the same order, right? Someone might go out in nature searching for letters of the alphabet, and they might come across an A first, then a B second, then a C third. And someone else might go out in nature searching for letters of the alphabet, but the first thing they saw was a C. Then they saw an A, then they saw a B. We want to be able to say that they both found the same thing, right? So that's why sometimes a set, just how you discover it, you'll discover it in a different order, but you don't really care. You actually just care about what is in the collection. You don't care about the order. You don't even care about if it was repeated. There are times that we do care about this though, that we do care about order and we do care about repetitions. And so for that, we need another kind of mathematical object. This object is called a tuple. It's not a word that people see often, so let me actually write down a pronunciation there. Pronounced tuple. So a tuple is a collection of objects. It's usually called entries to make it sound different from a set, but it can also be called elements. Sorry, my phone is ringing in my ears. called elements in which order and repetitions matter, right? So there are times when we want to pay attention to this. So the notation, it's similar to sets, except you don't write curly brackets, you write like regular parentheses. So something like A, B, C, D, E, F. This is not the same as the set with A, B, C, D, E, F, right? So again, can be named via letters. And you use regular parentheses. And order matters. So I want you to appreciate that this is not the same as something like B, A, C, D, E, F. It is also not the same as something like B, B, A, C, D, E, F, right? These are considered very different, right? It matters that the A is first in the top one, but it's not first in the second one. And it matters that the B is repeated. Sometimes we care about order and repetitions. Let me give you an example. A nice example would be, example, let's say we're looking at your grades in a class. So I can list your grades. It would not be good to list your grades as a set. It would be much better to list them as a tuple, because one, I would want to know which grade applies to which, because there might be different percentages applied to different types of grades. So I can have something like this, where this guy, the first entry is representing test 1 grade. The second entry is representing test 2 grade. The third entry is representing like the final exam, right? It matters that you got 95 both times. It's not like if you got a 95 on test 2, then I suddenly just ignore your test 2 grade. That doesn't actually make any sense. I wouldn't do that. So it's not like, oh, you got the same number you got last time. Like, I'm ignoring this. You have no test 2 grade now. Like, no, you got 95 both times. I want to record that you earned a 95 both times. You got 95 twice. And I don't think of that as something that, oh, I should throw away this data point. It also matters that I know that the 95s you got were relating to tests as opposed to a final, which means if I put an 89 in the first position, that 89 is no longer your final grade, it would be your test 1 grade. And that would matter because the final has a different percentage than the in-class test. So it actually matters who is in what order. So there are going to be times when it actually matters, right? And expressing this as a set is not good. So G, big G, equals the set of 95, 95, 89. First of all, you would ignore the repeat. Repetition ignored. Now that is a problem. This means that there's a loss of data. Also, the order doesn't matter. So can be reordered. So now which grade applies to which category? Right? So sure, if I'm trying to do an abstraction of amenities in an Airbnb, listing it as a set is totally fine. I would ignore repetitions anyway, and there's no intrinsic order to amenities in a room that you're renting. However, if I'm talking about grades in a class, there's definitely a priority, right? The final exam is worth more than other things, and the order matters. And it's possible for you to get the same grade on several assignments. And just because you got the same grade doesn't mean I should ignore those grades. So yeah, a set would be a bad idea to represent grades in a class, but a tuple would be a good idea. And vice versa, a tuple would be a bad idea to represent amenities in an Airbnb. Because then you're talking about, oh, there has to be intrinsic order and I can repeat things and it's fine. So I can list my Airbnb and say, I have 1,000 amenities. And really it's just me repeating Wi-Fi 9,999 times and then putting that I have a bed as one of them as well. It doesn't work. And this is going to be important when we get to probability. A lot of probability first starts by conceptualizing things as sets, counting things in those sets, and then coming up with an answer. And it will matter if the thing you're looking at can be conceptualized in such a way where, do I want it to be able to count repeats or reorderings of this thing? It's going to matter. And so that's going to be important. Yeah, I think that's all I wanted to say about that. Yeah, let's talk about a quick definition, just a term that I may or may not use. It might slip out, but I don't think the term is in your textbook, but it is something that I might describe things as, so I want you to know what it is. Definition, more like a term thing. Suppose n is an element of set of non-negative whole numbers. If A has n elements, so it's just a certain number of elements. It could have 5 elements, could have 7 elements, could have 13 elements, could have 1,000,000 elements. A has n elements. It is called an n set. If a tuple T has n entries, it is called an n tuple. So if I have A equals 1, 2, 3, 4, E, then A is a 5 set. If I have T equals A, B, C, then T is a 3 tuple. Okay. What else do I want to talk about? Also, if maybe I should actually define this. The size or cardinality of a set A is the, I'm going to put in quotations, number of elements in A. It is denoted this or this, which I'm pretty much never going to use a second notation, the N of A thing, but I think your textbook might. The writing absolute values is far more common. So, and that's what I'm used to writing. That's what I would write. And so now, if N is one of these guys, a non-negative whole number, and the size of A is N, then we say A is a finite set. Otherwise, so this means its cardinality is just some positive whole number. The amount of things in it is some positive whole number. Otherwise, we say A is an infinite set. So, example, if I say A is ABC, this means the size of A is 3 and A is finite. If I say boldface N is the set of all non-negative whole numbers, then how many things are in there? Well, an infinite number of things. You can literally count forever and you'll never finish. So N is infinite. Other than common sets of numbers, like the counting numbers, the whole numbers, we will not be focusing on infinite sets. Turns out set theory can get pretty weird when you throw infinity in the mix. And you only need to look at the history of set theory to understand how serious that statement is. There are a lot of brilliant mathematicians who literally drove themselves insane studying set theory and who had mental breakdowns of all sorts due to set theory. George Cantor, the father of set theory, had his own modern tragedy when he came up with a lot of these things that we use today in set theory, which no one questions it today. It's like, it's totally, yeah, that's totally, of course, right? Back in the day when he used to come up with these things, he was ostracized. Like everyone was like, you call yourself a mathematician? Like, what are you doing? This is ridiculous. Like, this can't be true, right? So he was ostracized and he had a very tragic time, despite the fact that he actually put in a lot of good work and a lot of our understanding of set theory due to George Cantor. Then you had other guys like Fager, I forgot how it's pronounced. But he also came up with a lot of the stuff with our concept of number, or what a number is and how to think about it and how to use sets to describe numbers. And there was also another very famous philosopher / mathematician, Bertrand Russell, who's the genius who's often like, I'm gonna destroy this man's whole career with my curiosity. You know, he'd always write people letters asking them stuff about their work, totally like send them off into a spiral when they can't answer the question. So that I really like your research on you know, numbers and sets and all that stuff, but then it got me thinking, you know, what if we were to create a set that contains all sets that are not members of themselves. Would such a set contain a member of it? Would be a member of itself? Totally, like he trying to figure that out and trying to make that consistent with his theory, like drove the guy to a mental breakdown. So I mean, sets, they're pretty dangerous. Handle with care. As such, because I don't want to be responsible for the deteriorating mental health of anyone in this class, we're going to ignore infinite sets for the most part, because it can get quite strange. I'll talk about some strange things with infinite sets next time, but not a lot. We're pretty much never going to talk about them again after that. Yeah. So let's move on to another definition. You'll notice here that I included 0. So you might be thinking, well, can a set have 0 things in it? The answer is yes. We call such a set the empty set. It is denoted by like a 0 with a slash through it, or more archaically, like an empty set of curly brackets. I would normally write the 0 with a slash through it, and most modern math textbooks would write the 0 with a slash through it. It's really very, very classic to write it with the empty brackets, and most people just won't do it. It's just too much work. So that's what it is. So it's a set with no elements in it, which again is completely possible. You can say, you can try to create a set, but you give an impossible condition, right? So remember, sets can be created or described via conditions, like here, right? I can say, I want the set of all alphabets in the English, set of all letters in the English alphabet between A and F inclusive. But I could easily say, I want the set of all blah that doesn't make any sense. I want a set that contains all sets. Is such a thing. It's actually impossible to construct such a set. I want the set of all people in the class that are over 12 feet tall. It's not so much that it's impossible to create that set, but that set would have no one in it. Like you just open up the brackets to start throwing people in, but you're going to realize, oh well, there's no one to throw in actually. It's just an empty collection. There's the set of things that does this is empty. So that's a thing. We also have another definition here. Define what it is for to be a subset. A set A is called a subset of a set B if every element in A is also an element in B. Right? We write A subset of B. So this says A is a subset of B, or A is contained in B. That's where the like C symbol comes from. And we can say it's potentially equal to B. Which is what this little line on the bottom represents. If A is a subset of B, but it is known that it's not equal or cannot be equal, then we write just a C without anything under it. It's like a very elongated C like this that you would see in a textbook, but when you're writing it by hand, you don't really notice. And A is called a proper subset in this case. This case being this case right here. So that's what a subset is and what a proper subset is. I should tell you some facts regarding subsets. For any set A, the empty set is a subset of A. When you think of subsets, you want to sort of think of it as like sub-collections. It's like someone already made a collection, they took a collection of stuff, and then you want to go and create a collection from their collection. So you just want to go and you want to choose things out of their collection. So subset, you can think of this as a sub-collection. So it's a collection garnered from a previously made collection, right? So this is a subset. So it turns out that the empty set is going to be a subset of any set by that definition, because out of a set of things, it's possible for me to try to create a subset, but choose nothing out of those things. So again, I can look at the set of all people in this class, right? So that would be a set. I can have a set, I can throw all your names in. And then I said, okay, from this set of all people in this class, I want to select people to put into another set, right? And how I'm going to make the selection is I want to select all the people from this class that are 12 feet tall or taller, right? In which case, no one in the class fulfills that property, in which case you cannot select anyone from the set to put in this new set, in which case now that new set you just created was empty. You've created an empty collection of things. So the empty set is a subset of any set. Here's another fact. For any set A, I don't know why I capitalized it, but I did want to emphasize it. For any, I probably shouldn't capitalize it. For any set A, it is also a subset of itself. Remember, the definition of subset is every element that A is a subset of B if every element in A is also an element in B. But then you look at A with itself in relation to itself. Well, every element in A is also an element in A. Like that just follows right away. That just has to happen, right? So every set is a subset of itself, and the empty set is a subset of every set. By the way, this includes the empty set. So the empty set is a subset of the empty set. And the empty set is a subset of the empty set because of this second fact here, by the way. Right, so there's nothing you can choose from the empty set, but you can take the whole thing as a subset, in which case the empty set has to be a subset of itself. Another fact. A equals B if and only if A is a subset of B, and at the same time, B is a subset of A. If everything that is in A is in B, and also everything that is in B is in A, then they have exactly the same things in them, and that satisfies the definition of equality. Okay. What do I want to do? Maybe an example for some of these concepts. Suppose A equals, let's make the set 1, 2, 3, 4, 5. B equals 1, 3, 5. C equals A, B, lowercase c. D equals 1, 3, 4, 5, 2. E equals, let's say, the empty set. Then we can say things like B is a subset of A. We can say things like A is not a subset of B. We can say things like D is a subset of A. We could also say that D is a proper, no, D is not a proper subset of A. I can say E is a subset of A. I can also say E is a proper subset of A, right? I can also say, in fact, I can say D equals A because they are equal here. Contain the same elements, but they are just rearranged. So I could say all of these things. Okay. What else do I want to tell you about? Power sets. The power set of a set A is the set of all subsets of A. It is denoted. There's a fancy P, and we put P of A in it. So here's an example. Let's say my A is the set 1, 2. Then I would be able to say the power set of A is going to be, it is itself a set I think I wanted to refer to that. It is also a set, but it's the set of all subsets. So we know that the empty set is always a subset of A, and we know that the set itself is always a subset of itself, right? What are the other possible subsets? Well, out of the collection of 1 and 2, I can make a sub-collection that only includes 1, but not the 2. I can also make a sub-collection that only includes the 2, but not the 1. And so that's the power set. So I gave you some other sets. B is equal to A, B, C. C is equal to the empty set. And suppose D is equal to the set containing the empty set. Okay, someone quickly tell me what's in the power set of B. Quickly, because we're pretty much out of time. B is that. Can someone tell me one element in the power set of B? Give me a possible subset of B. Anyone? Bueller? You guys there? Are you guys hearing me, or am I, or can I not hear you? Because I thought the audio was okay. Can someone speak to make sure that I can hear you and that you're hearing me?
I can hear you.
Okay. So you just don't have a guess then.
Would the empty set be in it?
Yeah. Can you think of something else?
A, B, and C in one bracket.
So the empty set and the whole set, yeah.
And then each of them by themselves.
Anything else?
I think that's it.
There's no other possible sub-collection? No other possible way to pick things from that set and create other mini sets?
Could you do like A and B together?
Yeah. What else?
And then A and C. And then B and C.
Anything else? Turns out that's it, right? That's all possible subsets. Right? So I want you to understand what a subset is and what a power set is and how to actually construct them. B, the power set of C. Okay, so it is itself a set. What is in that set? Well, C is the empty set, so there's nothing inside it to actually put in a set. But we know from the fact that a set is a subset of itself. So you can put the empty set itself in that. And so that's the power set of the empty set. As for D, D is the set containing the empty set. So clearly the empty set itself is a subset of that set. And I can take that set itself. So that's the power set. Now, here's a theorem. If the size of A is n, then it turns out that the size of the power set is 2 to the n. And you can realize this from all the previous examples, even though it's not a proof, but you can kind of realize it. You can kind of see examples or illustrations of it. When A had size 2, the power set had size 4. That was 2 to the 2. B had size 3, the power set was of size 8, which is 2 to the 3. C had size 0, the power set had size 1, this was 2 to the 0. D had size 1, the power set had size 2, 2 to the 1. If you look at all these answers, you'll notice that that was the case. So the setup, there are always 2 to the n subsets. Now, we're going to end here, but I just want to just quickly talk about why this is the case, because it's introducing an idea that we're going to be using later that I want you to start getting used to. Why? It's because for each element in A, we need to make 2 choices to create a subcollection. These choices are either yes, include this element, or no, do not include this element. So, I mean, for example, in the case where we had our A is equal to 1, 2, what I could do is I could list all possible choices for 1 and 2 in this set. I could say, do I include 2? Yes, or no, or yes, or no. Whereas here, yes, yes, no, no. These are all possible combinations of yes and no's. Whenever my answer is yes to both, I get the entire set. If I say yes to the 1 but not to the 2, I only get the set containing 1. If I say yes to the 2 but not to the 1, I only get the set containing 2. If I say no to both, I get the empty set. You'll notice here there are 4 elements because there were 2 elements, each of which had 2, let's put this in green, choices. So if you look at this as like a diagram where you think of the first thing to include, and the second thing to include, here you have 2 choices for what to pick. For each of those 2 choices, you have 2 choices for what to pick for the second guy. So this leads to you multiplying the 2's and getting 2 to the 2 equals 4. So the above is a counting principle known as the multiplication rule. And we will revisit at some point, not today. We'll revisit this. But the idea is, if you know how many choices you have for each stage in something that you're building up, like a set, then the number of possible kind of things you could build is going to be the product of all the different options that you could have. So yeah, if you have 2 choices for each thing, you multiply all these 2's, and that's going to be the case with creating any subset. So that's why you get the 2 to the n. You're just going to multiply 2 by itself n times. So yeah, we will end there. Thank you for your attention. But yeah, so a lot of information dump. It's not something that you will need to understand why it's the case. It's just something like you should just know these things. This is just what we call them, how we describe them, and that's going to be important for later. So that being said, thank you for your attention. I will see you guys in tomorrow's class. See you in the next one.